Hi. So this is the last lecture of this week. I thought I would let you know something I don't usually tell my students. The first time I took calculus, I was in 10th grade. I skipped ninth grade. I went to this kind of special public high school, kind of magnet school, and uh, I completely flunked calculus. I was kicked out of the class. So I took the textbook and I did every single problem in the textbook. And it took me all of the spring to do that. And then I took the AP exam. And I'm probably the first person in the history of the AP exam, uh, which, when the AP exam in those days was sent by snail mail to the advanced placement people, it got lost. And so I remember them calling me up on the phone and telling me that my exam was lost in the mail and that I should come to this building in Manhattan. By the way, I was born in Brooklyn, New York, and I should come to this building in Manhattan, this very tall skyscraper, and take the exam again. Now, this was the 1970s. And so I remember getting on the train, it was probably July, and it was extremely hot. And I go into this building, and it's like, I don't know, 70 floors. And the elevator was out of commission in this building. And so I go through the stairwell, and I have to go up like 30 floors. And I remember looking at this building and realizing this building is not going to last, because from the very ground floor of the building in the stairwell, there was this massive crack going all the way up to the top of the building, and you could see it all the way up. And I was pretty scared, and I took the exam thinking the whole time, I hope this building stays up. Well, the building stayed up. I took the exam, and I actually did really well. And even though I flunked out of calculus in 10th grade, I got a perfect score on the AP exam. So it just goes to show you. The reason I mention this is a math course, and it's a problems-oriented course. And the only way you're going to get good at this stuff is if you actually spend a lot of time practicing problems. And if you're having trouble with the problems, I mentioned that you should get in touch with the Math Resource Center, the MRC, and you can schedule help that way. And they're very, very professional people. So let me get started with my lecture today. I'm going to talk about, I'm going to finish off 7.1, just a few problems, and then I'm going to move on to the beginning of 7.2. So let's get going. Okay, so 7.1, continued. And let's do the following problem. It's a warm-up. The integral of x squared e to the power of x dx. Okay, this is not a hard problem, but you'll see that it requires more than one integration by parts. So we can let u equal x squared, then du is just 2x dx. dv is e to the x dx. So v is e to the x. And when we do this, we get what? U times v, which is x squared e to the x. And then we get v du, the integral of v du subtracted off, that's e to the 2x e to the x dx. Okay, so now we have this other integral to do, which looks a little easier because the power of x has been reduced by 1. So we go over here and we consider the second integral, the integral of 2x e to the x dx, which we're going to do by parts. So we'll let u equal, say, 2x. du is 2 dx. dv is e to the x dx. So v is the antiderivative, it's e to the x. And so this integral is 2x e to the x minus the integral of 2e to the x dx. Oops, I have to erase that. That's a typo. And that's 2x e to the x minus 2e to the x. And then we'll add the c later when we do the final answer. So there's going to be a plus c coming into this later. Okay, so now let's substitute that back in. We'll get the integral of x squared e to the x. What are we substituting? We're substituting into this expression here. Okay, and so so it's x squared e to the x minus the quantity 2x e to the x minus 2e to the x. And then we could add a c on the outside. And in fact, let's see, we can even simplify this. It's e to the x times x squared minus 2x plus 2, and then plus c. So that is the first problem. We did it, and that is, that's good. Okay, and I think, I just want to check to see I got all the signs correct here. It looks good. Okay, so great. So let's do another problem. Okay, so the next problem I want to do is problem number 43 on page 491. And it tells us what to do. It tells us to first make a suitable ordinary substitution to simplify. The integral here that we're looking at in the problem is e to the square root of x dx. We have to integrate that. So it says first make a substitution, and then after the substitution is made, we can do integration by parts. Now there are two choices we could do that I can think of here for a substitution. We could let u be the square root of x and then proceed that way, or we could let u be e to the square root of x. Now I tried the first choice, and this leads to something that can be done, but it's complicated. So I'm not going to do it that way. You can actually do the second substitution. It works out much, much, much better. So what if we do that? So in order to do the substitution, we have to compute du, and that's e to the square root of x. And then we have to take the derivative of the square root of x because we're using the chain rule. And the derivative of square root of x is 1 over twice the square root of x, because it's like 1/2 x to the minus 1/2, and that's 1 over 2 square root of x. And there's a dx here, of course. Okay, now we're not in a position to do the substitution yet because we don't have a 1 over 2 to the square root of x inside the integrand. However, we can multiply 2 square root of x on both sides to get 2 square root of x du is equal to e to the square root of x dx. Now, we have to get rid of the x that's sitting here, this x here, on the left-hand side. We have to get rid of the square root of x. So how are we going to do that? Well, notice that if u is the square e to the square root of x, then ln of u is the square root of x. So we can replace square root of x by ln of u. So we get 2 ln of u du is equal to e to the square root of x dx. Now we're ready to go ahead and substitute back into the original integral to get the integral of e to the square root of x. Well, that's u, right? And then oops, that's not what I wanted to do. I wanted to do this. We have so we see that 2 ln of u du is e to the square root of x dx. So we're going to use this expression here. The right side is our integrand, so we can replace it with the left side. And what do we get? We get twice ln of u du is equal to our integral. Now we have to integrate twice ln of u, but that's the same thing as twice the integral of ln of u. And if you recall back last time, we computed the integral of ln of x dx. And what we got when we computed that integral is, if I remember, it's twice, I'm sorry, it's not twice, it's x ln of x minus x plus c. So I'm going to substitute that. I just have to change x to u here. So this is twice u ln of u minus u. We could put the c on the outside if we want. And now we have to go back finally, and we have to go back and deal with the original substitution we made. U is the square root of x, so it's twice. Let me expand it out. Square root of x ln the square root of x minus twice the square root of x plus c, and that should be the correct answer if I didn't mess this up. Did I mess this up? Oh yeah, I messed this up, because it's not the square root of x here. U is e to the square root of x. So I'm going to put here e to the square root of x, and ln of I didn't even do this part right. Let me do this again. So what is u? U is e to the square root of x. And what's ln of u? That's the square root of x. Okay, so now this is correct. Okay, so that is the final answer to this problem. We're done with that. Okay. Let me continue then. Okay, so now I considered 7.1 as having been finished. We'll return to these types of problems, of course, all through the course, because this is one of the techniques of integration we're developing. And this is one of the very important techniques. It's used all the time. Okay, so now I want to start the next section of the text, which is section 7.2. So what's that about? Trig integrals. What I mean by that is integrals with trig functions in them. So in this section, we're, at least at the first part of it, we're considering integrals of the form where we have a power of the sine function, an integer power of the sine function, say sine to the power of m of x, times cosine to the power of n of x dx. So this is what we're going to consider. And I'm going to talk about several cases of this problem. And just today alone, case 1 is when we're going to consider m, the power of sine, to be odd, an odd power. So let's start off with an example. The integral of the cube of the sine function of x. And now n will take to be 0, so this is a special case of the general situation. So here is the trick that you do. You take the odd power and break off a factor of sine x. So this is sine squared x times sine x dx. And now we take the remaining even power of sine and convert it to cosine, power of cosine. So because I'm using the identity up here, sine squared x plus cosine of squared x is equal to 1. So this is 1 minus cosine squared x times sine of x dx. Okay. All right, so now you stare at this and you see, aha, we can do a substitution, and that looks like it's going to help us. We can let u be cosine of x, and then du is sine x dx, or the minus sign. But there's no minus sine x dx. There's only we have to change the sign by multiplying both sides by -1. So minus du is sine x dx. And now what I'm going to do is I'm going to take this expression and substitute it into the integrand entirely. Okay, so here we go. So this is, okay, so u is cosine x, so you get 1 minus u squared times minus du, because sine x dx is minus du, and this is the same thing as, I'll continue over here, the integral of u squared minus 1 du, and that's u cubed over 3 minus u plus c. And finally, we go back and resubstitute the value of u, which is cosine x. You get cosine cubed x over 3 minus cosine of x plus c. And that's our final answer to this particular problem. Okay, so that's an example when m is odd. I'm going to do another example now when m is odd, but let me clear the screen. Okay, so let's try. Okay, so the example I want to do next is sine cubed of x times cosine of x dx. Now we can proceed the way we proceeded before by breaking off a power of sine to make the remaining powers even. But it's actually easier here to just do this particular problem directly because the power of cosine that appears is just 1. We can actually do this by just letting u be sine of x, then du is cosine of x dx. And if we do that, we can do the substitution. This becomes the integral of u cubed du, which is u to the 4th over 4 plus c. So we get sine to the 4th over 4 plus c. We could do it the other way as well, but this is actually easier. It's much more quick. So I think we'll just go to another example. Okay, so let's try something a little harder. The integral of sine cubed of x times cosine squared of x dx. Okay, so let's follow the rubric that I mentioned. In this case, the power of the sine is odd, so let's break off a sine x. So we'll get sine squared x times sine x times cosine of x dx. Very good. And now I'm going to change the sine squared to 1 minus cosine squared to get 1 minus cosine squared of x times sine of x times cosine of x dx. And then we're going to let u be cosine of x. And then we get, if we do that, du, du will then be negative sine x dx. So negative du is sine of x, as we had before. So this is going to become the integral of 1 minus u squared times, we have a sine x dx coming from here, and we have a cosine x left over, so there's a u from the cosine x, and then there's the minus du from the sine x dx. So this becomes, if you expand it out, it's going to be, it looks to me like u cubed, and then minus, plus, is it u plus u cubed? Let's see, u cubed, and then minus u du. Okay, so let me fix that up. So what do you get? We get u to the 4th over 4 minus u squared over 2 plus c. And then finally, we go back and resubstitute the value of u, which was sine x. So we get, no, the value of u is cosine x right here. So we're going to get cosine to the 4th x over 4 minus cosine squared x over 2 plus c. There you go. So that's the solution to that problem. Okay, so I guess what I'd like to say is formulate is this general rule in this case. So let me summarize what we've done so far. Okay, summary so far. We want to integrate sine to the power of mx cosine to the power of nx dx, where m is odd. The steps are uh, write it as write sine mx as the product of sine to the m minus 1 x times sine x. So we broke off a power of sine, and now the m minus 1 that appears here, this m minus 1, is actually an even number. Okay, and so then we can use the trig identity, which replaces sine squared by 1 minus cosine squared. So use the identity sine squared is equal to 1 minus cosine squared of x. So that's what you do, and then you use the substitution u equals cosine of x, and that will do it for you. So that's the case where m is odd. Okay. So what about so that's the first case. Let's talk about case 2 now. That's case 2 is n is odd. Now, if both are odd, both cases, you can use either method. Now, what happens when n is odd? Well, what you're going to do is just do the reverse, right? So you're going to split off, split off a cosine x factor, and then use the identity cosine squared x equals 1 minus sine squared x to convert it into, and the substitution is u equals sine x in this case. So let me do an example of case 2. I think I'm going to need some space for this, so let me get a new whiteboard. Okay, let's try something like the integral of sine squared x times cosine cubed of x dx. So that's our example. Okay, so what is the procedure here? N is 3 and m is 2. So we're supposed to break off a factor of cosine of x. So sine squared x, cosine squared x, cosine x dx. And now we convert cosine squared into 1 minus sine squared. So sine squared x, 1 minus sine squared x, cosine of x dx. Okay, and that's the same thing. So we're going to let u be sine x, we said, and then du is cosine of x dx. So that's the du, so that's going to be u squared times 1 minus u squared times du is the integral. So that's the integral of u squared minus u to the 4th du, which is the same as u cubed over 3 minus u to the 5th over 5 plus c. And then we resubstitute the value of u that appears right here. And what do we get? We get sine cubed of x over 3 minus sine to the 5th x over 5 plus c. And there you go. So that does it. So in my next lecture, I am going to handle the case when both m and n are even. And that's a harder case, I admit, but it can be done. And in order to do all of these the problems in this section, the kinds of integrals that arise, you have to be kind of strong on your trig identities. If you don't understand your trig identities, if you don't know how to manipulate them, you're going to be in trouble. So take care. I'm signing out now.